Okay, let's talk about chapter 17, which is about analyzing the light that comes from the stars. So we'll talk about the brightness of a star, the color of a star, the spectra, the color spectrum that we see of that color, and then how we can use the spectra to measure all the properties of a star. Okay, so the luminosity is the intrinsic brightness of the sun. For example, Sirius is 25 times brighter than the sun, so we use the luminosity of the sun as a new variable, and we say that Sirius is 25 times the luminosity of the sun. So obviously, Sirius is a tiny star in the sky, even though it's 25 times brighter than the sun. Its distance is the key here. It's so far away that it appears to be way less than 25 times brighter than the sun, and that's because of its apparent brightness. So the apparent brightness is what a star looks like from our vantage point here on Earth. Okay, so when you look into the night sky, you see a whole bunch of different types of stars, different brightnesses. Okay, so we use the magnitude scale to measure the brightness of a star. So, for example, the sun actually has a magnitude of like minus 27. Okay, the scale goes from minus up until plus. And the more positive number, the higher the positive number, the dimmer the star, the more negative the number, or the smaller the number, the brighter the star. So full moon is negative, sun is negative, Venus is negative, Sirius is negative, Jupiter is negative, Alpha Centauri is right at 0. You can see things about 6 magnitude and less. Naked eye stars are visible of 6 magnitude or less. So if you look up stars with 6 magnitude or less, you should be able to find those on a given night, as long as it's clear out. Okay, all right, so if you look at this picture, beautiful picture here, notice you've got red stars, you've got white stars and yellow stars and white stars and red stars and red stars and blue stars and blue stars and all different colors of stars in this picture. So what's going on there? Turns out that the color of the star is related to the temperature. So a blue star might be 25,000 Kelvin, a white star is going to be 10,000 Kelvin, a yellow star like the sun is going to be about 6,000 Kelvin, an orange star is about 4,000 Kelvin. So here's some examples of some stars. Okay, and Betelgeuse, a red giant, very red star in the top left of the Orion constellation, 3,000 Kelvin, very low temperature star. Okay, let's see. So the spectra of stars and brown dwarfs. So we sort stars by their temperature, and the spectra classifications we give them are O, B, A, F, G, K, M. Okay, so the brightest stars, the hottest stars are O, the coldest stars are type M, the sun is a type G star, and then there's brown dwarfs that have classifications of L, T, and Y. Okay, and the original classifications of stars were A, B, C, D, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, and so on. Then, as we started to reclassify them, and instead of starting completely over, we just rechanged the order because we changed how we were sorting stars. We decided to sort them by brightness and temperature rather than some of the hydrogen spectra that we see from the stars. And so the new system is weird. So yeah, there's this mnemonic that was created by Annie Cannon, who classified the stars, and she came up with, "Oh, be a fine girl, kiss me," and guy or girl. "Oh, be a fine guy, kiss me," whatever you want to put in there. That's a mnemonic, a way to remember this. "Oh, be a fine girl, kiss me." "Oh, brother, astronomers frequently give killer midterms." "Oh boy, an F grade kills me." Whatever. "Oh, be a fine girl, kiss me like that, yo." That's stupid. Okay, so each of the spectral classes is subdivided from 0 to 9. So the sun is a type G2, there's type G3, G4, G9, and so on. And that just allows you to subdivide between the classifications. Okay, so here's your spectral classes, O, B, A, F, G, K, M, and here's the temperature ranges for those spectral classes. Okay, so then here's just some examples of stars of the different types. The sun is again type G star there, Betelgeuse is a type M. It's a red giant. Rigel, very bright star, 10,000 Kelvin. Okay, so what the main thing is that a blue star, so here's your O, B, A, F, G, K, M. So these are all stars. These are all different stars. So this might be Rigel up here at the top, and the sun is here in the middle, and Betelgeuse is down here. Okay, and in this, Betelgeuse is a red star, so it's got a lot of emission down in red and not a lot of emission out in blue. So what we're looking at is a single row of this is the full rainbow coming from the sun. And you can see that the rainbow coming from Betelgeuse has a lot of red light in it, but not a lot of blue light in it. As you go up to Rigel, it's got a lot of blue light in it, but not so much red light. You can see as we go up the scale from M to type O, you can see that the colors kind of sweep that direction towards the blue. So a star, as it gets hotter, will go from red to white to blue. And the bluer it is, the hotter the star is, okay? Blah, blah, blah. So spectral classes, L, T, and Y, are for brown dwarfs. So if you're about 8% the mass of the sun or less, you don't get hydrogen fusion. And so if you don't have that, you don't get a full star. So we can sometimes call brown dwarfs failed stars. They're just, you've got something from a planet all the way up to a star, and you've got everything in between. And so there's a type of things, it's right between Jupiter and the smallest stars, and they're called brown dwarfs. Okay, if Jupiter was a little bit bigger, it could be a brown dwarf. If Jupiter was about 80 times bigger, it could be its own star. Okay, but it's not. So Jupiter here, look at it, it's about the same size as this guy. The difference is this has a little bit more mass, so it has a little bit more density, and is actually, there is some fusion going on in here, but it's not hydrogen fusion, it's deuterium fusion, and that is what differentiates a planet like Jupiter from a dwarf, a brown dwarf like WISE 1828. Okay, so here's that difference spelled out. Okay, so we can determine the size of a star. We can determine all kinds of stuff from looking at the spectral lines. Okay, so if you remember, emission lines versus absorption lines. So this would be an absorption spectra of the light coming from, let's say, a white dwarf. Notice that the absorption bands, these vertical missing pieces taken out of the spectrum, they're very wide. They're not very narrow. Whereas for a very large star, these bands are very thin, those absorption bands. Okay, so that's just a way for us to determine, hey, we noticed that the spectral lines, the emission and absorption lines are very different for small stars compared to big stars. So we can determine the size of a star just by looking at its spectra like that. We can determine how fast the star is moving by looking at the Doppler shift. Again, we find these absorption lines, and notice that when you're stationary at rest, your absorption line is here at about 652 nanometers or so. If the star starts moving away from us, you see that line gets shifted to the right. And so it's no longer at 652, it's at whatever that is, almost 670 or so. And this one here, when it's coming towards us, it gets blue shifted towards the blue end of the spectrum. So when we talk about red shift and blue shift, notice that the red line doesn't become blue, or the red line doesn't become red. It becomes slightly redder or slightly less red towards the blue. So that's what we mean by blue shifted and red shifted. It's not actually turning completely blue. The lines are just being shifted around depending on the velocity. Okay, that's the same Doppler effect caused by like a race car coming towards you. It starts as a high-pitched, and as it passes you, it goes down pitch. So at rest, it would sound like, that's what the car would sound like. If it's going away from you, it's going to go, and when it's coming towards you, it's going to be as it goes past you. So the pitch is going to be a little higher, or, sorry, a little lower or a little higher, depending on whether it's coming towards you or away from you. Same thing with light. The light will be a little bit bluer or a little bit redder, depending on how fast the object is coming towards you. Again, most of these stars, they're not noticeably different colors. You have to really look at the spectrum to see the red shift and blue shift. And then, okay, so stars, there's a thing called proper motion. This is a picture of the Barnard star, which is flying around in space. It's the fastest moving star in the sky. You can see all these other stars in the background are barely moving, but in the 20 years that this was taken, Barnard's star moved from there down to here across the sky. So pretty cool to be able to see that the stars are not just static out there in space. They're actually moving around, and that motion is called proper motion. Same thing here. This is what the Big Dipper looked like 50,000 years ago. This is what it looks like now. This is what it's going to look like in 50,000 years from now. Okay? So that's called the proper motion. We can tell if a star is rotating because the emission lines get smeared out, as half the lines from here get blue shifted and these lines get red shifted, and then you have your central line. So they get a little bit smeared out compared to a star that's not rotating. So that's just another way that we can use the light to determine properties about the stars. Okay, and that's the end of chapter 17. So again, stars have an intrinsic brightness called luminosity. How they appear from us is called the apparent brightness, though, and we use a magnitude scale from that, and 6 or less you can see with your naked eye. And it goes negative is the brightest stars. Okay, stars have different colors, and the colors correspond to their temperatures. They also have color spectra, and we classify them by their color spectra. Type O are the bluest stars, type M are the reddest stars, and L, T, and Y are our brown dwarfs. Our sun is a type G2, and that's kind of a medium temperature star, 5,000 Kelvin. And then we can use those spectra to determine lots of things about the star, including how big a star is, whether it's rotating, its proper motion, and whether it's what types of things it's made out of in its atmosphere. Okay, see you guys later.